All right, good morning, everyone. Hope you guys can all hear me. Can someone just write in the chat box that they can hear me? Okay, great, thanks. All right, let's get started. We're on page 16 here. We're looking at Euler's method. And this is kind of like a combination of um, slope fields and or content or involving slope fields and um, linear approximation. Because we're going to be using a differential equation to approximate a solution to equation. So uh, now, if we had the function in front of us, then we can just plug in a specific x value and to get the y value. Um, but let's say, there are differential equations that we're not able to find solutions for, at least not algebraically. So we have to rely on the derivative to help us kind of move along and find a value piece by piece, but we're doing it using approximations. So on the first page here, page 16, I'm just going to kind of walk us through visually what's happening. But when we move into page 17, or a problem that we're going to be able to have to do on the quiz as well as on the AP exam, it'll be a lot more condensed, a lot more uh, easier to work through, a lot more organized. But for now, I'm just going to kind of show things step by step, but moving forward, we're not going to be doing it quite this way. So number one, dy dx equals 1 plus y. So this is our slope formula for this curve. And y of 0 is equal to 0. So we have an anchor point. We have a starting point. And our delta x is 0.5. So we're going to be stepping through the curve and incrementing 0.5 at a time. So using Euler's method, show an approximation to the solution curve y equals f of x. So first, we're going to construct a tangent line at 0, 0 from 0 to 0.5. So we just have to figure out, we have our ordered pair. We're going to figure out the slope at this point and then use that information to help us map out what is y value, what is the approximated y value at 0.5. Okay, so here is our equation. We're just basically going through point slope form. Now our slope is coming from this dy dx. So we know that our dy dx at 0, 0 is equal to, now there is no x value for us to plug in, so we're just going to plug in 0 in for y. So 1 plus 0 is 1. So we have our slope, we have our ordered pair, and then we'll just do point slope um, from this point moving forward. So y minus 0 is equal to m, our slope is 1, times x minus 0. So if we clean this up, we'll get y is equal to x. So that is our equation of our tangent line. And if we were to plug 0.5 into this tangent line, we were going to get 0.5. So y of 0.5 is equal to 0.5. So that's our new point then is 0.5 comma 0.5. So from 0, 0, we're moving to 0.5, 0.5. Now, our eventual goal is we're trying to figure out where is this graph going to lead when we get to 1.5. Okay. So we're just kind of inching along. Now that we have this point, we're going to repeat the same process. We're going to find the slope at this point using our differential equation, and then we'll build another tangent line equation to figure out what our next step along the way is. And then we'll repeat this multiple times until we reach our approximated y value at 1.5. So now step two, we're going to construct a tangent line at our new point. We'll plug this into our differential equation to get our slope. From there, we'll build our tangent line equation. And from there, using that new line, we will find our approximated y value location at x equals 1. Let me go ahead and find the slope first, since we already know our ordered pair. So our differential equation is still the same. It's still 1 plus y. So we have our slope, we have our ordered pair, and now point slope form. All right, give me 1 second. I think some students are trying to get in. Okay, sorry about that. So we have our slope using our same differential equation. So we have our slope is 1.5, our order pair is 0.5, 0.5. And now let's build our tangent line equation. And if we clean this up, we'll get y is equal to 1.5x minus 0.25. So now that we have our next updated tangent line equation, at this point, we can plug 1 in to our tangent line equation to get our next updated order pair. So now our next set of order pair, it was 0.5, 0.5. Now we're able to move to our next point in our approximation, which is 1 comma 1.25. So 1 comma 1.25, somewhere here. So now our last step is we're going to take this, we're just repeating the same process here. We're taking our next up order pair, plugging it into our derivative to get our slope, and then plugging in the 1.5 into our equation to get our approximation using this method. So we're going to start at 1.25. Take that order pair, put it into our differential equation, our slope formula, and we get 1 plus y, or y is 1.25. Sorry, yeah, 1.25, which is 2.25. So we have our slope, we have our order pair, point slope form. Solve for y, and then plug in our destination at 1.5. We'll get 2.375. So using our previous order pair, we're now able to reach our estimated value where our curve would be at 1.5. Now, this is only an approximation. We don't have a function to work with. We only know our initial starting point, 0, 0, and then we have our differential equation to kind of help guide us along in terms of using the slope at every updated point to kind of inch along and move to our destination. So at 1.5, it ends up being 2.375. So kind of tell that this kind of mirrors what we see in our, if we're able to if we're able to be given this actual equation, we can see that our process is kind of looks like what we're trying to get towards. Okay. But again, this is only an approximation. So the main idea here with Euler's method is that we're using multiple tangent lines, and each tangent line is going to have an updated slope using the differential equation. Our approximation of the point on the solution curve will be closer to the actual value. And the idea is that if the smaller our step size, the more accurate our approximation. Because if we take smaller step sizes, we're able to gather more information from the differential equation at these individual steps, and we're able to make more make more incremental adjustments to eventually arrive at our approximation. So this is the visual way of kind of showing what's going on. But now that I've shown this, the way that we're actually going to be working the problem is going to be more abstract, but it will allow us to get through our problem faster. Okay, all right, next page. All right, page 17. Here's a way Euler method questions often appear on the AP exam. So you're going to be given a derivative equation. This is how we're going to find our slope. And our function is equal to y is a solution to this differential equation. And we're not going to be given the solution to the differential equation. We're going to have to use the slope and our anchor point to kind of move our way along. So our anchor point in this case is f of 1 equals 3. You're always going to be given a starting point to begin with. So this is your anchor or your beginning point. So if our order pair given to us is 1, 3, what is the approximation to f of 2 obtained by using Euler's method with 5 steps of equal size? So we want every step to be the same, and we want to spread that out over the course of the distance from 1 to 2. So to find our step size, we're going to be using this formula, b minus a over n. We're taking our full width and dividing it into 5 equal steps, or n equal steps. In this case, n is going to be 5. So our delta x is going to be, my a value is 1, my b value is 2, so 2 minus 1 divided by 5, which is 1/5, which is 0.2. Okay, we're going to be using this table here. On the quiz, on the AP exam, the table is not going to be drawn for you. You're going to have to kind of draw your own sketch, build out your own table. But for now, I'm going to have the table built for us here. So in your first row, you're going to put your starting point. So your starting point is 1, 3. And we're going to keep going until we reach, well, we're going to work this X column and keep incrementing by our step size. So we're going to keep adding 0.2 until we reach our destination, which is at X value 2. So 1 plus 0.2 is 1.2, plus 0.2 is 1.4, plus 0.2, 1.6, 1.8, and finally 2. Okay, let me talk about how we're going to arrive at these values. We're basically just going to be working our way through each row. And once we're done with the first row, we'll move on to the second row. And we'll keep going until we reach our destination. What we're really looking for is the y value associated with this x value too. So once we get to this step or this value, we can stop. That's our answer. We're not going to be involving the last set of y prime and new y. So think of y as your starting point, your y sub 0. Your y prime is basically the result from your dy dx or your f prime, whatever the derivative equation that's given to you. We're going to use that to help us find basically our slope. And then the new y is going to be found by kind of incrementing through linear approximation. So we're going to be using this point slope form, this linear equation to help us get to our new y. So let me just show you what that looks like. Y minus y sub 1 is equal to m times x minus x sub 1. Think of this y sub 1 as your initial y value or maybe the previous y value. So if I solve for y, I would get y sub 1, or I'm going to call it y sub 0, plus m times x minus x sub 1. And my x minus x sub 1 is basically my step size. So this is going to be my delta x. So basically y sub 0 plus m times delta x. So to find our updated y value, we're just going to take our previous y value that's given to us, and then plus m, or our dy dx, times our step size. Okay, so one piece at a time here. To find y prime, our tool that's given to us is this dy dx equals 2x. So x, we can pull that. If it needs both an x and y, then we're just going to pull it from the row that we're on. Our derivative here only needs an x, so we're just needing that 1 there. So 2 times 1 equals 2. That's our slope. And now we can find our new y value. So y is equal to y sub 0. That's just going to be the the current y value that we're on, which is 3, plus m, that's our slope, delta x, that's our step size. Okay, we can use our calculator here. 3 plus 2 times 0.2, that's 3 plus 0.4, which is 3.4. So we have our y value that we can use in our next row. So the new y value that we found is now going to be the starting y value for our next point. So whatever is here, you're going to copy that down to the y value on your next row. So now we just repeat the process. We're going to take our order pair. In this case, I guess we don't need the y value. We just need the x value. Repeat the process. Take that order or take that x value, dump it into your derivative to get your updated slope at that point. Take that 2.4, that's our slope, and now put it into our tangent line equation. Our current y value is 3.4. Our updated slope is 2.4. And our step size is always going to be the same, 0.2. Well, for this problem, 0.2. All right, calculator, we get 3.88. And we're just repeating the process here. Plug 1.4 into the derivative, get your slope. Point slope form. Get our updated y value, bring it down to the next row. Go back to your derivative equation, get your updated slope. Point slope form. Two times 1.8. Now, once we have 5.8, we can stop because that's our goal, right? We're trying to find our approximated value at f of 2. When x equals 2, our y value is 5.8. And this is still just an approximation. It's not the exact value. We don't have the equation to plug in. So this is our approximation using 5 steps. And obviously, if we could do 10 steps, then the approximation will be even better because we're able to gather, update our information with a derivative more often. Um, So this is basically the process. Sometimes the information that's given to you may be a little bit, just be maybe different variations of of what's given here. So I'll just do a couple of examples, how some of the information presented may look a little different, but it's the same process. We're always going to be gathering the same set of information and moving our way through the table. Okay, let me just do maybe one or two more examples, and then I also want to try to squeeze in a revisiting of L'Hopital's rule. Okay, so let's do practice problem number 1. This is on the bottom of page 17. Okay, the table below gives the value of f prime, the derivative of f, if f of 1 equals 2. So here we have our starting point. What is the approximation of f of 2.5? So this is our b value. Here, our a value is 1. And with 3 steps of equal size, that's our n value. So really, our first goal is to make sure we can get our step size set up. So delta x is b minus a over n. So 2.5 minus 1 all over 3, which is 1.5 over 3. 1.5 is half of 3, so my delta x is just 1/2, 4.5. Okay, let me build my table here. This is my x, this is my y sub 0, this is my f prime or delta x, sorry, or dy dx, or slope, whatever you want to call it. And then this is how I'm going to get my new y value. Okay, so we start with order pair 1, 2. Let's build out our delta x until we reach our destination. So we're going to keep adding 0.5 till we reach 2.5. This is where we want to be at the end. Trying to find the approximation to 2.5 when x is 2.5. So we're trying to get to this point. Once we fill in this box, then that's our answer. Okay. Now this one, I think we can save a little bit of time because they're giving us the f prime at these locations here. So here I'm trying to find f prime at 1, and f prime of 1 is 0.3. So we don't have to plug in like in this instance where we have to actually do this manually. We're able to just pull it from the table. So f prime, or our slope, is simply 0.3. Right? F prime of 1 is 0.3. And now our y value is y sub 0, which is our current y value, plus m, or slope, times our step size, 0.5. Use your calculator, and you'll get 2.15. Take that new y value, which will now be the starting y value for our next row. Okay, next up, we're trying to find f prime at this location. So f prime at 1.5 is equal to 0.7. Y is equal to, up our current y value, in this case is 2.15, plus our slope, 0.7, step size, 0.5. We get 2.5. Take that 2.5, bring it down to the next row, repeat the process. Now we're at 2, so f prime of 2 is 1.2. Take our current y value, and we get 3.1. So 3.1 is our answer. We can say using Euler's method, our approximated y value at 2.5 is roughly 3.1. Okay, let me do one more with you. Well, one more from this section. Uh, Everything else kind of looks the same, but 5 looks a little bit different. So if you can turn to page 18, let me do number 5 with you. So this is page 18, number 5. Okay, they give us h of x is equal to the integral from 1 to x of the square root of 1 plus t squared dt. So this looks a little bit different here. Um, X equals 1, that's our starting point. Find h of 3, and then we want 2 steps. Okay, let's find our step size. Delta x is b minus a over n. My a is 1, my b is 3, and my n is 2. Okay, so in this case, our step size will be a nice integer of 1. In this case, h prime is going to represent how I'm going to find my slope. And then my y is y sub 0 plus f prime or h prime or m times delta x. Now, normally they give us an ordered pair, but they only give us x equals 1. So I need to find my starting y value. They don't give it to us, but they do give us a function for us to plug in and find the y value. So I can plug 1 into the function to get the y value. So the integral from 1 to 1, well, that's nice because if the bounds match, then I know that my value is just going to be 0. So we know that h of 1, because the integral from 1 to 1, we haven't moved. So we know that's just going to be 0. So we have to kind of do an additional step to find that y value. Now our step size is 1 as well. So we're going to keep adding 1 until we reach what we're trying to find. So 2 and 3. So we're trying to find h of 3. So we're only going to take 2 steps. So we're just trying to get to this y value. Once we're here, we're done. Now, we want to plug 1 into h prime to find the slope, but they don't give us h prime. We have to find it ourselves. So to find h prime, I got to find the derivative of this function. Okay, now should remind us of second theorem. We know that derivative and integral will cancel each other out. Just have to plug in the upper bound into the variable. So h prime is just going to be square root of 1 plus x squared times the exponents or times the upper bounds derivative. X's derivative is just 1, so that's not going to change anything. So h prime is just going to be square root of 1 plus x squared. Okay, so this is going to be our formula now to find our slope. at these respective points. So let's do h prime of 1. Which is equal to square root of 2. We have our slope. We have our order pair. We have our step size. Let's update our y point. Our current y value is 0. Our slope, or our h prime at that point, is root 2. And our step size is 1. So root 2 times 1 is just root 2. There's my updated y value. We'll do this process one more time. Now we're going to plug 2 into the derivative to find our slope. The derivative only requires the x value, so I just need to plug the 2 in. So 1 plus root 5. Let's update our y value. So our current y value was root 2 plus root 5, that's our slope, times our step size, which is 1. And that's just going to be equal to root 2 plus root 5. I'll just leave it in that form. So we can therefore conclude, using Euler's method of 2 step sizes, our h of 3 is approximately root 2 plus root 5. Okay, with time remaining, I just want to revisit L'Hopital's rule and just do maybe just one um, example here. So if you can turn to page 14 in your packet. So we know how L'Hopital's rule work, right? We know that it's always going to be involving a limit, and it's the idea that if we evaluate a limit and we get 0 over 0 or infinity over infinity, it gives us that green light to take the derivative, the numerator and denominator, and then reevaluate the limit. Right? So this rule is going to work great, but it only works if we can get it into the form of 0 over 0 or infinity over infinity. There are other indeterminate forms that we're going to have to be responsible for in BC. And that can include something that looks like this. If something is 0 to the 0, or if it ends up giving us 1 to an infinity, or infinity minus infinity, or 0 times infinity, or infinity to the 0, if something looks like one of these forms, uh, we can still use L'Hopital's rule, but we kind of have to manipulate it so that it can get into that 0 over 0 form before we can jump into we have to get it into a fractional form, basically, and produce 0 over 0 in that form in order for us to use L'Hopital's rule. So what I want to show you is really a problem like example 2, something that is in the form of 0 raised to the 0, or if it gets us 1 to the infinity, or infinity raised to 0, we can rewrite our equation, use log differentiation. So I just want to do one example with you. This is example 2 at the bottom of page 14 here. To A. Now, if I try plug infinity in into this form, I get 1 plus 2 over infinity, which is 0, right? 2 over infinity is basically 0. 1 raised to infinity. This gets us that strange form that is indeterminate, but we want to do L'Hopital's rule, but it's not quite in the form that we um, uh, can really apply it. So what we're going to do is we're going to explore this function for a moment. So we're going to step to the side and just think about, okay, what can I do if this were the function that we're working with? Now, anytime we have a variable raised to a variable, and we want to do something with a derivative, we know that, well, we have to basically get that variable in a different spot, right? We have to go through log differentiation that allows that x to come down. So we're just going to kind of play with this equation for a moment. And let's take the natural log of both sides. Now that we're inside a log expression, we can bring that exponent down in front. Now, our goal really, we're not trying to find the derivative just yet. We're just trying to get this to look like a numerator over denominator so that we can hopefully get, we basically want a 0 over 0 to show up from our original equation. Our goal is to use L'Hopital's rule. Right. So we're going to play with this form for a moment. So the hope is, what can I do to manipulate this so that I can get something as a numerator over a denominator? So this is what we're going to do. We're going to force that x in the denominator and make it 1 over x. So we're going to do this. Right, that seems strange, but dividing by, if I want to divide by 1 over x, that's the same thing as multiplying by x, right? We're just forcing that x to live in the denominator so that I can maybe create a situation that L'Hopital's rule can work. Okay, now I'm going to rewrite this now as natural log of 1 plus 2x to the negative 1, just getting myself ready in case L'Hopital's rule can work. Now, limit as x approaches infinity. If we were to now do the limit in this form, again, let's plug in infinity in for x. 2 over infinity is going to be 0. 1 plus 0 is 1. Natural log of 1 is 0. So this is 0. If I plug infinity in for this x, that's also 0. So this gives me the form that I'm looking for. This does produce 0. So this gives us now the green light to do L'Hopital's rule. I have my equation set up now to do my derivative process. So here's my next step. So my derivative, using L'Hopital's rule, u prime over u. So negative 2x to the negative 2 all over 1 plus 2x to the negative 1 all over negative 1x to the negative 2. Okay, so this is our derivative. We're going to try to reevaluate and see if we can get a real number out of this. Let me clean this up a little bit. Dividing by this is the same thing as multiplying by the reciprocal. So this cleans up. The x to negative 2 cancels out. Let's reevaluate the limit, what we have left. The negative 2 and negative 1 will just become a 2. Negatives cancel out. So now if I reevaluate the limit, the hope is that this is now going to get us a real number. So if I plug infinity in for the remaining x, this will give me 0 because my infinity is in my denominator. So 1 plus 0 is 1, which gives us 2 over 1, which is 2. Now, we're not quite there yet. We're almost there. But remember how we manipulated this to do log differentiation. It comes from this natural log of y. So we're ultimately trying to get to y by itself. We took the natural log so we can bring that exponent down. So now the result is that natural log of y equal to 2. Okay. And now our goal is to get y by itself because that's ultimately what y is equal to. We have the limit at a stage of it, but it's not quite there. So then if I want to get y by itself, I can raise both sides with e as the base. So y is equal to e squared. This is the limit that I'm looking for. Because I took the natural log of both sides to get it into a form that I want to use, I have to bring it back in terms of the function that we're working with. So my limit of this function is equal to e squared. Okay, thanks everyone. So your homework due on Monday will be from the previous section. So page 11 through 13, page 46 to 49. I'll send out a reminder on Sunday. And I'll also send you a link to this video if you need to rewatch it. All right, have a great weekend, guys. See you on Monday.